going to demonstrate here how to use the BayesNetBP ShinyApp. The first thing is to load the library. The library can be installed from CRAN directly. And once it is loaded, I just want to take a look here to show you the different functions within the package. Okay, and the Shiny app is actually right here, Run BayesNetBP app. So let me just do a question mark to bring up the help page. So this is all the information that you need to know about the app. So here we're going to use this, launch the browser, set it to true. The input object is a cluster tree, and this can be imported directly into the app interface. So there are a few libraries that you need. I have already installed these libraries. I'm just going to run this piece here. I'll get some warning messages here, but this is nothing. You have one particular library, Cytoscape, which is needed for the visualizations, and this can be installed using this command from GitHub directly. So now let's launch the app. I'm just going to copy and paste this, and this is the app. This is the interface. I'm just going to widen my window a little bit here. So this is the default network that will appear in the window when you launch the app, and you can play with this network a little bit to get a feel for these different operations. More likely you'll want to import a cluster tree object, which I'm going to do right now. I've got a few different cluster tree objects here. I'm going to import this one. This is from our paper, and it's a yeast example. It's from an expression QTL dataset. And if I hit update, so I've loaded it in, I hit update, and now I can see that this has changed. Okay, so this is the yeast network. So let's just start with this panel here. Okay, so if we focus on this panel here, this is kind of for exploring the graph. And you can see that I can put my marker over here. And as I do that, as I scroll over these different nodes, they're appearing here in the selected nodes. Other things I can do, I can zoom in. Okay, I can zoom out. I can use my mouse to make things larger and smaller too. And I can use this toggle to move things around. Okay, so the subgraph feature is very handy, especially if you have a large graph. So I'll just kind of demonstrate that right now. So if I take a node and I click on it, okay, so I've taken this node, and maybe I want to expand this graph from this node, either up or down, looking at the parents of this node or the children of this node. So this is the DAG, and I'm going to go, let's say, up. Okay, now I've highlighted all the parents here, and I can even go up one more. And now I'm going to just keep moving in this direction, right? And what I can do is use this add to list. This is going to take all of these things that I have highlighted and add them to a list, which I can use then to subset the graph. Okay, so now I have taken my original graph, I've zoomed in on a particular region, and I can reset that if I want to. So I can do the same thing, and I can go down the graph. Okay, so let's see here. And if I want to expand it, now I'm going to the children nodes, and I can keep going down if I want to. And I can add these to a list and subset that list, and here I have now a subgraph. And in addition to extracting subgraphs, which is very useful when you have a much larger graph that you're looking at, we can also click on these nodes and we can move them around to make our visualization a little bit easier. Okay, so I'm just going to reset all of this here. The other thing that we can do is we can choose a layout, and so there are two layout options. Okay, this is one and this is another. Okay, I'm going to stick with this first one for now. And like I said, you can also move these things around. Okay, So this is the Bayesian network. This is the directed acyclic graph. And if you're using BayesNetBP, usually you will have this information or you'll be learning it using another package, but you want to perform probabilistic reasoning with the network. And so although this first panel is largely concerned with exploration of the graph, it's going to come into play a little bit later too. As a first step, let's think about setting some evidence in the graph. Okay, so suppose we want to set some evidence. Perhaps we observe something. So let us think that maybe we observe this node here. So I'm just going to find it here. PPAP2A, this is a gene. And let us set some evidence for this gene. So this is actually standardized data. So I'm going to set this as maybe 1.5. Okay, so the range is roughly between -2 and 2. And so I observe this at 1.5. What I can do then is I can add evidence. Okay, and I've added evidence to the graph. And I have in this cluster tree object a elimination tree, which is used to do this probabilistic reasoning that we're going to do. So the point is that we have entered this evidence and we want to understand kind of the system-wide response or the system-wide effect of this evidence, or what the most likely states of these particular nodes would be in light of this evidence. So this is the goal here. So I've entered this and I'm going to absorb it. Okay, so once I hit the absorb key, that evidence is absorbed into the cluster tree object. And the first thing I'm going to do is observe the shift in marginals. Okay, so this is going to tell us how things are changing, what direction they're changing in, and how much they're changing. So let's just click on this. Okay, so now you're going to have some color here. And if you are to take your mouse and kind of go over these different nodes, this is a SNP marker on chromosome 1, and it's changing actually quite a bit. The JSI is the Jeffrey signed information. It is a measure that we use to quantify the change in the distributions of these individual nodes. So you can see by the color what is changing the most. Darker means you're seeing the most change. Positive means that it's going up. Okay, so in other words, when we observe PPAP2A at 1.5, this particular node, the mean is likely to be higher. So it's moving up from where it was. And so we can maybe click on this node, and we can see that the JSI is 1.152. The blue is indicating that things are going down. Okay. So this gives us a holistic view of the entire graph. Now, if we really want to understand what's happening in these different nodes, we can use plot marginals to understand these individual changes. Okay, so let us suppose we want to understand maybe ApoA2. So now I'm just going to click on this. Okay, I see what the JSI is, but maybe I want to see how the distribution changes. This is going to set it into this. This is the selected node. I've kind of gone over it. And when you go over a node, as I start to move my mouse, you will see this changing accordingly. So here it's ApoA2, this is HDL. Okay, so let's look at HDL. Okay, so we'll plot the marginals. This is going to specifically zoom in on HDL. Now in this case, HDL is a discrete variable. It's categorical variable, high and low. And I can tell that because the way that BayesNetBP plots the discrete variables, the categorical variables, is in a box. Okay, and the circle ones are the continuous variables. So this is telling me actually that before I absorbed evidence for PPAP2A, PPAP2A. These are the frequencies, if you will, of HDL for high and low. Okay, so they're actually just about the same. Now, if I take this evidence into account, then I see this change quite a bit. Okay, so now it's much more likely in this case when PPAP2A is 1.5, it's much more likely that there would be a low HDL in that case. So this is what the discrete or the categorical variables look like if you want to look at their individual distributional changes. Now we can do the same type of thing with the continuous ones. Of course, we'll have a density if we do that. So again, I can click on this node and I see it. I have to be careful not to go over nodes because it will automatically change them. That's one thing you need to be careful of. But if I put over here, if I click on it, it will also send it over here. But I just don't want to overtrace any other nodes because it will overwrite it. So I just need to make sure I have my node of interest here. And now I can do the same thing for the continuous node, plot the marginals. Okay. So the same idea. This is before the absorption of PPAP2A. We can see what the distribution looks like. And after I absorb that evidence and I propagate it through the network, which is what is happening underneath this app, what we see is a shift in distribution. Okay, so we see it was the node DGEGS was pink, so I know that it's going to be moving up in mean, which we see. We see the red is after. So we see a slight shift, and we see a little bit of difference in the variance too. So the estimation, the marginals are updated according to the new parameters that are inferred after the propagation, based on the propagation. Okay, so that gives you an impression of how you can explore the network using essentially these two panels. The other thing I want to mention is that, let me just reset this, okay, and I want to just clear this evidence out, okay. So let's say I want to absorb evidence for PPAP2A as I did before. And maybe I want to absorb another piece of evidence. So we can certainly do propagation with more than one node being observed. So let's say that we see this one is 1.5, and let's see we also see ApoA2 as -1. Again, this is standardized. So I can add that evidence, and it's here. And what I need to do is the same thing. Absorb it, and now they're going to both turn green. And now let's observe the shift in marginals. Okay, so now the pattern has changed, right? Because we have absorbed in two different places in the network, and we can see that there are big changes in these brighter nodes, if you will, and more subtle changes in the softer colors, and we see the direction of change by the actual color there. So we have red and blue. So we can do the same thing as we did before if we're interested. Let's say I want DEGS1. Again, I'm going to just kind of toggle over here, and I see that I've selected that node. I can plot the marginal, and I can see what the changes are like. Okay. All right, so that kind of gives an impression for how to deal with a single piece of evidence or two single pieces of evidence. So now let's reset things. Okay. Another thing that BayesNetBP will do is it can consider a spectrum of evidence. Okay, so in this case, what I mean by this is we can choose an observed variable just as we did before. Okay, for this one we can only do one at a time, but let's say we are going to pick on our PPAP2A again. And let's say, you know, before we use 1.5, but let's say we want to look at how things change as I range PPAP2A over -2 to 2. Okay, so this is where I can fix the range of values that I'm considering for PPAP2A. And I can also change the step. So this is going to just take steps of size 0.5 between -2 and 2. And then I'm going to ask the same thing. How do these other variables, how do the distributions, the marginal distributions change when PPAP2A is observed in this interval? So instead of a single graph, we could imagine that this would be a spectrum of evidence. And what I want to do, this is going to tell me what variables I want to plot. And I'm going to actually add all of them. Okay, so I'm going to visualize all of these things as a function of changing evidence in PPAP2A. So let's just plot what this would look like. Okay, it might take a moment, and this is what we see. So here we have a way of visualizing. These are all of the different nodes in the network. And this here is the Jeffries information as it was defined over here as well, and also in the paper. So we can see that when we change PPAP2A, this is as how the shifts in marginals occur over the network. So in this case, we can see, for example, NEU1 is the most changed. Okay, so absorbing information in here is obviously going to have a very strong impact on the child node. But then we see some other shapes as well. And yeah, like I said, we can only do this for one variable at a time because we can only really visualize this as a function of one variable and the Jeffrey signed information. You can think about things in 3 dimensions, but we have not gotten around to coming up with 3-dimensional plots to support that type of visualization. Okay, so I think that's all I wanted to describe. I hope that that helps you get started using BayesNetBP. Thanks.